Hi everyone, we're just gonna wait I guess a couple more minutes for people to join and we'll get started. Thanks everyone for joining. Okay, let me share my presentation and I think it's time to get started. We have a few people that have joined again. Thanks everyone for joining. Oh, layout to what? Let's see, focus only. Okay, I hope I've done the right thing. So let's get going. Cool. So my name is Panagiotis Antonopoulos. I see some familiar faces in the audience. Thanks so much for inviting me to talk in this conference. And I'm excited to cover the work we've been doing for the last 2-3 years in the Azure SQL database group or SQL Server on accelerated database recovery. So this, as I said, has been an ongoing effort for the last 3 years. We're now pretty much mostly done with the improvement, and we'll discuss today what it looks like and what were the challenges, how does it work, and so on. And let me first clarify that by database recovery, we're referring to the process of bringing the database to a transactionally consistent state when a crash occurs. So let's say your system has been running fine for a while, but power goes down, a failover happens in the cloud or something like that, and now we need to run the database recovery process before we can bring your database online. So let's see what SQL Server's recovery looked in the past before our work, right? So for more than 20 years, SQL Server has depended on the traditional ARIS recovery algorithm. You might be familiar with that. It's an algorithm from the 90s that has been widely adopted by most commercial RDBMSs. And this depends on what we call write-ahead logging. So we store data and logs separately, and we make sure that any operation, let's say I'm inserting a row or I'm updating a row, this is logged in the log stream first, and only then is updated in the corresponding data pages. So the logging part is synchronous, and then in the background, there is a so-called checkpointing process that takes all of the data pages and flashes them to disk. And this checkpoint effectively guarantees that if there is a failure, if we crash, we don't need to go and start replaying everything from the beginning of time. We have checkpointed our latest, or at some point, fairly recent point, we have checkpointed the database state, and we can just start our recovery from that. And the recovery is pretty much split in 3 phases: analysis, redo, and undo. And let's take a quick look of what this looked like, again, traditionally, right, before the accelerated database recovery work. So the first phase, as we discussed, is the analysis phase, and this starts from the last checkpoint. So I don't know how familiar where you are with the different settings that exist in SQL Server, but you can configure how frequently you want checkpoints to happen at the high level. So every, let's say, few minutes or seconds, even depending on your settings, this checkpoint process will come, and it will again flash the current database state on disk, so that when we recover here, we need to analyze what has happened since this last successful checkpoint, right? So the goal of this process is to identify any transactions that were uncommitted when the crash happened, so that we know that these transactions need to be rolled back, but also identify what was the oldest dirty page, right? As pages get modified, they get what we call dirty. So this process has this second goal of finding what is the oldest page that hasn't been flashed in the system. The next phase is what we call redo, where the goal is to reconstruct the full database state as of the time the crash occurred. So as part of that, we start, and in this case, we need to start the redo process from the beginning of the oldest active transaction, and that's where problems start. We will discuss in a second. But if I have a very long-running transaction, we need to start potentially hours ago, reprocessing all the log and trying to redo all of the operations. So we will reacquire all the logs held by this transaction, and then we also need to even update data pages again that haven't been flashed by the checkpoint process. Checkpoint again happens periodically. If something doesn't get flashed, or it hasn't been flashed in the last few minutes or whatever, it needs to be what we call redone, right? So at this point, at the end of the redo phase, the database is partially available, but any transactions that were uncommitted when the crash occurred will still be holding the logs that we reacquired here, as we discussed. And your database is technically online, but you can still not access bunch of tables, and you have to wait effectively for the third part, which is the undo process. And the goal of that is to undo back any modifications by these uncommitted transactions, right? So were in flight when the crash occurred, they now rolled back. And once this is proportional to the transaction size, right? If I had a insert operation, let's say that gigabytes of data, we need to go and undo every one operation of this, right? So as you can imagine, again, if the transaction ran for 3 hours, it might take at least as much to undo all of this transaction. I'm saying at least because the transaction might have used parallelism. So it's even more work for the single-threaded undo process. So this can take a substantial amount of time as well until it brings the database to a fully consistent state, and now everything is online, all logs have been released, and now you're good to go pretty much. You can do anything you want in your database. So what are the limitations of this? We've kind of already covered some of them, but as we saw, both the redo and the undo process are proportional to the size of the longest transaction, right? So again, in my example where we're doing a like huge bulk insert of gigabytes of data, and then a crash occurs, we need to come back, redo all of that, reacquire logs and so on, and then finally even undo everything, right? So if I inserted millions of rows, I need to remove millions of rows, and that can take a huge amount of time. Secondly, again, as we saw, all this process is based on the log. Let's see if there is some question. So all this process is based on the log, and with that in mind, now the log size is to the transaction size, right? So again, if I have transactions that run for hours, consider log gigabytes sometimes, and if you're using heavily SQL Server, you will have you can have transaction log terabytes of data if pretty much you're updating a huge amount of rows, you're doing large index rebuilds and so on. So this is the problem. And before we jump to our solution, let me also briefly introduce our what we call multi-version concurrency control. You might be familiar with it as the versioning subsystem of SQL or whatever, but it's a system that was introduced in 2005 to support snapshot isolation, right? If you're familiar with different isolation levels in database or SQL specifically, snapshot isolation allows you to effectively always read a consistent snapshot of the database. You can start your transaction and just read everything as of that snapshot. Even if concurrent updates occur, these are invisible to you. So you have very stable states to read from. Now, to achieve that, SQL Server, but also most databases, the way they do it is that instead of like updating every row just in place and overwriting the earlier value, we'll still do that. We'll update the row, but we will also preserve the older version in what we call the version store, right? So let's say we're bumping Nick's salary from $100 to $200. Pretty poor guy. So in that case, we will preserve the older value in the version store, right? And we create a linked list effectively of all these versions, so that if an older transaction needs to access that, it can traverse this version chain and find the appropriate version to retrieve from the database, from the version store. And until our work, all this was stored in SQL Server's TempDB, like temporary storage that is reset every time we restart SQL. So today, again, because it was used just for snapshot isolation, before our work on accelerated database recovery, when the database restarted, everything was lost. So none of these versions were preserved, and that was okay at the time because, again, it was just for snapshot isolation. So now you might be wondering, okay, you're telling us you've had this for 20 years, even the multi-version concurrency control is from 2005, so that's 15 years. Why did you guys spend all this time, all this energy to go and change this thing, right? And the easy answer and the quickest answer is because we're now moving to the cloud, right? We're betting big time on Azure SQL, and this has significant differences compared to on-prem environments, right? We are depending on commodity hardware that fails a lot more frequently than very expensive enterprise hardware. Also, I mean, because of how we manage our cluster deployments and so on, upgrades happen a lot more frequently now, every month. So definitely failovers are more frequent than an on-premise environment. You might be running SQL 2005 still, right? Well, now it's not supported anymore, but still 2008 or 2008 R2. I mean, you might be running the same environment for years, so without having as many upgrades, but that's not the case in the SQL world. Secondly, I mean, you might have seen our work on hyperscale, and this is to support cloud databases with terabytes, hundreds of terabytes of data. As the data grows, transaction sizes grow, and again, we can't get in a state just to be able to meet our SLA, right? We're promising 5 nines of SLAs in Azure or whatever. We can meet these SLAs. If somebody does a large update, we're running a deployment, like a software upgrade in the back end to improve the service, and suddenly there is an hour, 2 hours of downtime, right? That's unacceptable. And based on our telemetry that we collect across our database fleet, we saw that in 5.9 percentile, so 99.39s, was over an hour, and that might not sound too bad. I mean, it's a very small percentage, excuse me. But when you consider the millions of databases running in Azure, that starts adding up, right? And it can lead to pretty much unhappiness for some customers on frequent basis. Not individual customers will hit this repeatedly, but we keep having customers complain about it. So that's not an issue we want to deal with, right? And the biggest problem is there's nothing you can do really, right? So the customer was running this large operation, we did some deployment, and now they're stuck there. And that's definitely not the state we want. That's not the quality of service we want to have. We want to be able to provide our strict availability SLAs and fully meet them and have our customers satisfied. We also did a survey among many SQL customers from on-premises as well, and they pretty much reported the same things. So recovery time is proportional to the largest transaction. So if I'm running some huge operation and the database crashes, I get in trouble. Rolling back, like when I just roll back a transaction that's going on, has the same response. It will also take a long time if the transaction is long. And finally, again, if I'm running a huge index build operation or something like that, or even a large bulk insert or whatnot, the transaction log is proportional to the transaction size. So many of them reported, actually 60% reported they have experienced more than an hour of downtime due to recovery in their production workload. So, I mean, again, when we're thriving for 5 nines of availability, we really need to get away from this experience. So let me now introduce Accelerated Database Recovery, which is our new recovery scheme that combines what we described so far, ARIS, with multi-versioning concurrency control, so with this versioning subsystem, to achieve what we see at the bottom, right? So we want to achieve recovery at constant time, regardless of the transaction size of or the workload. We want to be able to recover the databases below 1 minute, ideally. Second, we want to have instant transaction rollback. So you're running a large transaction, something happens and needs to roll back, or you decided you made a mistake and you're rolling it back. We want it to be instant. We don't want to get blocked there and hold logs for hours, blocking the system, right? And finally, we want the transaction log size to be constant space as well. And that's important for, again, for Azure very much because we manage these resources, right? So if some customers need to run huge transactions, that's just their workload, it's very hard for us to manage it and make sure that we provision the right amount of log space. So by being able to bound this space, like keep it constant regardless of the workload, it's giving us a lot of flexibility in how we provision the resources. So we still use write-ahead logging from ARIS for durability. So that's how we make sure that if something gets committed, it's durably committed in the database. But we leverage the multi-version concurrency control now in a different way. We make sure that all data modifications are versioned. So regardless of whether you use snapshot or not, now everything is versioned. And what the main idea is that we use these versions. If a transaction rolls back or we crash, we use these earlier versions to access the committed state of the row without having to go this through expensive undo process, right? So the undo process, again, let's take a simple example. I inserted 10 rows, the undo process needs to remove these 10 rows. So we don't have to do that anymore. We store like the earlier version of every row, so we don't have to do the undo process synchronously. Any new accesses to the database can just retrieve the earlier version of the row. And finally, again, we mentioned that all data operations are versioned. SQL Server is a complex system. We have a large number of special handled, what we call logical operations or non-versioned operations. These are still managed using the log, but for that purpose, we introduce a secondary log stream that we call slog that manages specifically these non-versioned operations, and we'll cover more details in a bit. Let me quickly do a demo to show you how things look like, and then we'll jump into more details of how they're implemented. But let me check if there are any questions. Okay, I don't see anything, so let's go to the demo. So here we have a pretty simple demo, but I think it really demonstrates the power of accelerated database recovery. So we have two SQL Server processes running, one with accelerated database recovery on and one with off. And we're just, in this case, we're simulating a very large transaction by doing a very large bulk insert operation. So here we're seeing as rows get inserted. I mean, you'll see that pretty much the performance of the two instances is pretty much the same. This small difference is nothing important just because one of our workloads started a bit earlier. But if you see, they're growing at the same pace, so performance is the same. And in both cases, we also see that the transaction log size, for now, is growing together with the transaction size, right? So as we're inserting more and more rows, the transaction log size grows. And we see that both in terms of the absolute file size as well as the percent use. But let's see now what happens with accelerated database recovery, right? The green line is representing accelerated database recovery. So when it hit around 400 megabytes, although the old SQL Server without the accelerated database recovery continues to grow together with the transaction size, right? You see the red line keeps growing and growing, and the percent use also keeps fluctuating around 100%. So we hit 100%, we grow the file, and we keep growing and growing. In the case of accelerated database recovery, we're now completely stable. So that's what I was referring earlier of keeping the transaction log size bounded, right? And then we see here that the log space is not like growing as much. It stays about 50% use, and we don't need to grow the file anymore. So the transaction keeps running. We've reached now almost 2 million rows, but the log space is still bounded. Right? That's great, again, because we don't need to provision a huge amount of log space, either on our Azure environment or in your on-premise environment, you no longer need to provision terabytes of storage for lock. Now it's always bounded, so you don't have to handle that. Now, we have inserted about 2.5 million rows. I'll just kill the transaction. If I let it run for, or kill the SQL processes, if I let it run for longer, we're just going to see even longer recovery times for the non-ADR case. But let's just do it now. Recovery happening in the background. So now we killed the SQL processes, so we're simulating a crash and just restarted them. They're just coming up right now in the background. And in a second here, we'll see some diagrams popping up around recovery time, right? So actually what you can see here is that accelerated database recovery just completed. In less than 2 seconds, we finished the full recovery process. The database is 100% online right now. No locks are held, and you can go and just continue using your database with no impact at this point, right? As we can see now on the left side, with accelerated database recovery off, we're still at 1%. I mean, these mathematics here are not precise, so it won't take that long. But I guarantee you, again, it will take maybe minutes. If I let the transaction run for longer, we let it run for about a couple of minutes. If I let it run for half an hour to load a large number of data, it would take hours to recover, right? So I'll let this recover in the background. I don't want to waste more time here. And we'll come back a little bit later to see when the recovery will finish. But right now, your database is offline. So if you're not using accelerated database recovery, you're pretty much stuck right now, having to wait for recovery to complete. Coming back now to our presentation, let's see how do we achieve that, right? It's not magic. Let's see what is the what are the mechanics behind the curtain, behind the hood, to see how this happens. So we have 4 main components of accelerated database recovery. We have the persistent version store. Earlier we mentioned that we use versioning. So we use a persistent version store to store the earlier versions of the rows. And for each one of them, we'll get into the details. So let me just briefly introduce them and we'll get to that. We have a process that's called logical revert, and we'll see what that implies. We have the secondary log stream that we already mentioned for managing non-versioned operations. An example are like lock acquisitions, cache invalidations, things that cannot easily get versioned. They're not data, they're representing some logical operations in the database. And finally, because we maintain all the earlier versions of every data, every record in the database, we have the so-called version cleanup process that takes care of removing all of these versions in the background. So it doesn't impact your workload, but it runs in the background to remove all of the earlier versions that are no longer needed and reclaim space. So let's start by the persistent version store, or PVS. Again, as we mentioned earlier, in the old versioning subsystem of SQL, we used all of the we stored all of the record versions in tempdb, right, in temporary storage. That cannot work for our purposes because we want to use these versions for recovery purposes. If the database crashes and comes back, we want to be able to use these versions, and that's why we had to move the version store into persistent storage. So these versions are now stored as part of the user database. They're normally logged operations, so you will see, I mean, if you want to analyze the transaction log and see the details, you will see this version information getting inserted into the user database as part of this version store, and that allows us to make it recoverable after a failure, right? So if we crash, we can recover this version. And as an optimization, performance optimization, we separated the version store in 2 pieces. There is the in-row version store. So whenever there is space next to the row in the database, we'll just store the version next to the row rather than having to allocate new space and store the version. And that's both a performance optimization, again, because we don't have the overhead of like trying to find more space and so on, but it's also a space optimization. We will not use as much space because we'll just store the difference between the 2 versions in the row itself. So it's a lot more compact. And then we have the off-row version store, which seems a lot more like the traditional version store in tempdb, where we actually store the full row versions. In this case, we store them in a system table in the user database. This is a heap table in the sense that it doesn't have any indexes, but it's highly optimized for concurrent inserts. And that's an area where we have been investing a lot to make this as fast as possible to minimize the impact for your workload. So we'll pre-allocate space and like do a lot of magic to make sure that these inserts into the version store are rocket fast. The second part that's very important is what we call logical revert, right? So as we described, every update now, rather than just updating the row in place, it will also generate the version of the previous, it will also store the version of the previous version of the row. So the idea here is that when now, let's say there is a crash, right? So we have the latest version, which is the uncommitted one, and the previous version, that's the committed one. It should be visible to all transactions, right? So when a scan happens, a query happens, instead of just fetching the latest version, which is uncommitted, it will detect that this is an uncommitted version that eventually needs to be cleaned up, but it will just skip it and go to the previous version that is committed. So again, with this logic, we no longer need to do the undo process that needs to go and, again, revert or undo all of the operations. We can just skip them and go to the earlier version, that's the committed version. Now, when an update happens, however, we need a little bit more logic there to handle that fact, because we have the earlier committed version, and now in the middle there is this dirty uncommitted version, right? So there is what we call the logical revert process, that it's something similar like the undo process, you can imagine. So if you inserted a row and the transaction was aborted, it will delete this row. So similar to undo, it's doing compensating action to bring back the database, or bring back the state for this row to what it was before the database crashed. But anyways, it just does a small fix up there to bring the row in a consistent state so it can be updated. We saw a little bit of overhead by this process, so we actually applied a very interesting optimization that instead of having to always perform this compensating action, for a large number of cases, we can optimize that and just ignore the uncommitted version and just override it. So with that optimization, I have some performance results later, but what I'm trying to say is that without optimization, effectively we get back to the full performance of the system, even when there are uncommitted versions, right? So even if you inserted or you updated a large number of rows and you crash and now you come back, the performance of the system is very much on par with what it was before the crash or with today's recovery, and we'll have some performance numbers to show that. Finally, the logical revert process also handles what we call the aborted transaction map, or ATM, that tracks the state of every transaction, right? So when a transaction gets aborted because you're rolling it back or because a crash occurred, the state that this transaction was aborted is captured in the aborted transaction map. And this is checkpointed, and we can reconstruct it during recovery as part of the analysis process. So the goal of that is, again, since we mentioned that every query that comes to access the data, it needs to check if the data is committed or uncommitted, if the version is committed or uncommitted. That's how it does that. It will check the aborted transaction map. Now going into so we covered all the version stuff, right? How all versioned operations work. Again, they always update the row and generate the earlier version so that we can use the versions rather than having to do the undo process. But as we mentioned, there are lots of logical operations, non-versioned operations. And how can we handle this, right? I mean, if they're not versioned, we still need to undo them somehow. Some examples, again, I mentioned earlier, are lock acquisition. If a transaction acquires a lock, we still need to make sure that this is done. Or the transaction, as part of the transaction, we need to invalidate some in-memory caches and so on. We have a lot of caching, again, for performance, and how all this work, right? So for that purpose, and again, we don't have to use the transaction log for that, again, because we want to be able to truncate it and have the space bounded. We introduce a secondary log stream that's actually just in memory. And this tracks all of these logical and non-versioned operations. And again, these are very, very rare, right? So if you do a bulk insert that inserts, let's say, 100 million rows, you will still have just a handful of these operations just for initializing the operation, the table, and acquiring a few logs, right? So now we're going from gigabytes of log space down to just a handful of log records. And with that, we can store them in memory. They can be processed extremely efficiently during the undo or redo or undo process, or even transaction rollback. And these are stored just in memory as a linked list ordered based on the chronological order of this log record. So if your transaction generate 10 of them in a specific order, they will be stored in the same order, similar to the transaction log. And again, this is reconstructed during recovery. So when the checkpoint happens, we checkpoint it to the log, and we can reconstruct it as part of the analysis process. So with that, we can use it to recover the database. Again, we can use it during redo, undo. We can use that to undo any logical or non-versioned operations that cannot easily be versioned, and use the logical revert process. Cool. So before we jump, let me check if there are any questions, just to be sure. Okay, excellent. I hope it makes sense. Again, if you have any questions, please feel free to write them in the chat. I'll be checking periodically and at the end as well. So now with all this infrastructure, let's see what recovery looks like with ADR, right? So analysis is mostly the same. It will again start from the same point, the last checkpoint. So a pretty small amount of log that needs to process, but it has some additional goals now, right? We need to reconstruct the S log. So we see here at the bottom, we have the huge transaction log, which has number of log records, but it needs, like this gets just checkpointed and it gets reconstructed. So we only see in this case, for example, it has just 4 log records, right? And also it will reconstruct the aborted transaction map. So if there were any aborted transaction in the system, including transactions that were in flight when the crash happened and they were never committed, these are also effectively aborted. We will reconstruct all of these states so that we know what transactions in the system are aborted. And then the second part now has changed. It might not be as visible, but the key difference here is that this large phase, which we have to scan the log from the beginning of the oldest transaction, is no longer using the transaction log. It's the tran log. It's using the S log, right? So rather than having to process millions of log records, now in this example, it just has to process just 3. And again, as I was saying earlier, even in a huge bulk insert, the S log records are again only very, very small number to manage this non-versioned operation. So with that, rather than having to reprocess gigabytes of log, now it just redoes 3 quick log records from the in-memory S log stream. And then we only have to redo from the transaction log just again from the last successful checkpoint, right? So this gap here between these two dotted lines remains very much bounded, right? Because it depends on when the last checkpoint occurred. And again, that's something you can configure on premises or that we manage in the cloud, but it happens every few seconds or every minute. So it can keep this part here is very bounded. It's no longer proportional to the transaction size. It just captures the last few minutes, few seconds or minute of data updates that have happened. Now coming to the undo process, again, this is just processing the S log, so just a handful of log records that need to be undone. And at this point, your database is fully online, and that's where we saw the benefits in our demo earlier. The database came back in just 2 seconds with ADR. Let's go back and check if it has come up without ADR. Yes, it did. And it took 1.5 minutes pretty much to recover. You can see that both the redo and the undo operations took like more than 40 seconds, 40 and 50 seconds, whereas here it just took 1.5 seconds. Like huge difference. And again, the biggest problem is that these are proportional to the transaction, right? I just let this run for a minute or two. If I had let it run for half an hour, this would be in the half an hour ballpark or even more, right? Maybe even double that. So that's the important thing to keep in mind. Even here, though, with this just couple of minutes of run, we can see huge difference. Here, your database was fully available in 2 seconds. Here, it took 1.5 minutes. And if I let it run longer, it would have taken potentially hours. So now finally we have completely recovered the database, but there are still all of these dirty versions lying around in the system, and that's what the cleanup process is responsible for, right? So this is an asynchronous process that will run in the background. It's fully online, it doesn't impact your workload, and we run it on fairly limited resources, especially in Azure, where we manage the resources. We run it as a lower priority task, effectively, to not impact your main workload in terms of CPU and I/O. So there are 2 parts of it. There is the logical revert or an in-row cleanup that just visits all the rows in the data tables, your normal tables. So it will find any in-row versions that are no longer needed, remove them. If there are any versions by aborted transaction, it will perform the logical revert process we discussed a bit earlier. And the goal is to effectively remove all of these versions so that we can even remove the aborted transactions from the aborted transaction map, right? So we clean up the whole database. We do 1 pass to clean up the whole database and remove any transactions from the aborted transaction map. The second part of it is the off-row cleanup, version cleanup, that just visits the off-row version store we discussed earlier, the off-row PVS. And then it will also again similarly, it will find off-row versions that are no longer needed in the system and remove this as well to reclaim the PVS space and shrink the database file, the database size. So now let's take a look at some rough numbers. Again, here we're presenting the recovery times without ADR and with ADR for different types of operations, so insert, update, delete, and different number of rows updated, right? So we have 10 million rows, 50 and 200 million rows, again, inserted, updated, deleted. In the case of traditional recovery, you can see here that the recovery time is pretty much proportional to the size of the transaction, and it can take, it goes even to an hour in this case, roughly, for updating 200,000 rows. We can see that both the redo and undo parts are proportional to the transaction size. Now coming to the side of the ADR, you can see that in all cases we recovered the database in less than 15 seconds, right? Regardless of the number of rows updated, the recovery times remains bounded and very, very low, in the order of like 15 seconds or less. Similarly, coming to transaction rollback, this is the scenario where you run a large transaction, you realize something went wrong and you want to abort it, or an error occurred, like we're trying to insert a bunch of data and we run out of space, and this needs to be rolled back. Here, in the case of non-ADR, you'll see all the lines for insert, update, delete are proportional to the transaction size. The time it takes to roll back the transaction is proportional to the transaction size. Whereas in the case of ADR, these are all constant, right, and pretty much zero. So you just click the cancel button or roll back the transaction. That's pretty much instant. Like you can see here, the lines are all at zero. Finally, we measured the throughput of the system, right? Because we presented all of this work, like recovery looks great, but now how does it impact the performance of my system? So we evaluated with two types of workloads, TPCC and TPC. If you're familiar with that, these are, we didn't run the official benchmarks, but we used a very similar workload to evaluate, and these are OLTP transactions. So short transaction processing for, like one is simulating a retail store. TPCC is simulating an e-shop effectively that accepts orders. TPC is simulating a stockbroker firm, right? Anyways, very small transactions, but in the case of TPCC, it's more update intensive. So we can see here that with in-row versioning enabled, the optimization to perform in-row versioning, we have roughly 14% degradation in performance. So it's noticeable, but again, considering the benefits of around recovery times and availability, we believe that's definitely acceptable. And again, this is really a worst case scenario. Like this is a very, very update intensive workload. Most customers' workloads will not be as update intensive. In the case of TPC, which is more realistic, it has a more reasonable balance between reads and updates. We're just at about 2.5% of performance degradation with ADR, right? And we see here that also the in-row versioning optimization helped us quite a bit, especially when there is a large number of updates. But bottom line, again, for most workloads that are not as update intensive as TPCC, they have a more balance between reads and writes. The performance degradation is like. Now, also looking at the space usage, I won't go into the detailed numbers, but the main high-level idea is that the log size with ADR remains very, very low. So you see in all cases, it just remains even what we saw in the graph below 400 megabytes. In the case without ADR, it can grow into the gigabytes, and if your transaction is larger, it can go into terabytes even. And the size of the PVS also remains fairly bounded with all our optimizations for in-row and so on. We keep it quite bounded. So all of this logic was actually rolled out into production. That was a stressful in some sense time, but very interesting also. It's like having to roll out a new recovery algorithm for a production database that hosts millions of databases is definitely a daunting task. But we were able to roll it out with fairly minimal problems, I would say, minimal impact for our customers within just a few months. Right now, most of our database have it enabled, and we're talking about more than 5 million databases. And now, earlier we mentioned that the 5.9 percentile of recovery time was at 1 hour. Now it's down to 3 minutes, right? So even in the worst cases where customers are running huge transactions, we can bring back their databases online in just a few minutes, right, versus an hour. Also, we see the benefits around log space management. It now remains bounded. We no longer have to account for huge transaction log and provision for that. So that is also a very nice property in terms of us managing the resources. And again, I'm talking now from the Azure side, but you would see very similar benefits from your side running in on-premise environment. And again, this is available in Azure in SQL Server 2019 as well. you can see the same benefits. Very fast recovery times, fast rollback times, and very small log space. You no longer need to manage terabytes of logs. That said, I mean, there were some challenges. Again, among these 5 million databases, there are very wide variety of workloads. We saw a few issues, both in terms of performance as well as PVS size growing because we couldn't run the cleanup process fast enough. We've done a lot of optimizations in the last few months, and I think at this point we're at the place where we're managing both the PVS size, the persistent version store size, the aborted transaction map. Everything now is under like full control effectively. The same fixes are rolling into the SQL 2019 CUs and PCUs, so you should be getting them as well, and definitely in the next release you'll have the full optimizations I've been doing, and these are rolling out in Azure as we deploy new bits. Now, from your perspective, especially when running on-premise, in Azure we monitor these things more and manage them from our side. So we monitor both the persistent version store sizes, aborted transaction maps. If we see them grow, we'll file incidents and proactively investigate your database. So these are the benefits of running in Azure. But if you're running on-prem and you're doing your own database management, here are some troubleshooting tips that you can use. The first problem that you might notice is that PVS is growing, and it might be due to a long-running transaction or a query, right? So if there is a long-running transaction, we need to preserve the older versions to be able to roll back or for snapshot purposes. And you can see that this is happening by querying this DMV, sysdm tran persistent version store stats. If that happens, I mean, that's by design in some sense. We need these versions for the system to operate. So if these queries or transactions are expected to be long running, you need to provision a little bit more space for the persistent version store. We now allow putting the persistent versions in a different file group, so you can manage it more efficiently if you want. If they are not expected, you generally expect short transactions. You can identify them and remove them, like just kill them, as you would normally do with long-running transactions or sessions that could be impacting your system. The next problem that we've seen is the background process for very large database can run slowly, right? It can happen, it can take multiple hours, happen once a day, but during this time we will again see PVS size as well as aborted transaction size accumulating. And we've done a lot of optimization in this space to allow both cleaner to run faster, but also clean up more aggressively. But again, if your database is huge and you have a large number of updates, this can take a while. So again, during this time, you can monitor it using the DMVs, SQL tran aborted transactions, or the previous one that reports cleanup times and the size of persistent version store. But at the end of the day, if that happens, you have to provision again a little bit more space for PVS until the cleanup process completes. Or, I mean, if you really believe that I need to trigger this more aggressively, you can run the cleanup process on your own using this store procedure, SP persistent version store cleanup, and that will allow you to run on your own with pretty much unlimited resources, so that can run faster potentially. Finally, we mentioned that the slog log stream is in memory, right? So again, this is tracking very minimal number of log records, but as an extreme case, right? If you have a huge DDL transaction, DDL is referring to data definition language, schema changes effectively, right? So if you have a table with hundreds of indexes, 15,000 partitions in each index, this adds up to more than 1 million hobbits and row sets and partitions. I mean, this will take quite a few resources in terms of slog to be dropped. In that case, you might see memory increasing for the SQL Server process, and you can monitor how much of this is used by slog by running this query, effectively looking at DMOS memory clerks that reports all the memory usage and looking for a name like slog. It will report, we have a different memory clerk for its database, so you can see how much its database uses. We haven't really seen this becoming an issue even in Azure, but something to keep an eye on. Sounds good. So I think that's mostly it. We talked about accelerated database recovery, which combines Azure, ARIS and MVCC. We decouple recovery time from log space and log space from the user workload, so you can have huge transactions without impacting recovery time. And that are really, I mean, the goal was to meet our availability SLAs in Azure, but also simplify our resource allocation. And as we saw, it has pretty much minimal performance impact for most workloads. That was mainly it. I think we're right on time. So thank you so much. I'm happy to stay and answer any questions that you might have. I hope that was useful.